All right, ladies and gentlemen, welcome back to QCrypt 2022. Now we will proceed to contributed talks to be experimental talks. And now I would like to welcome our session chair, Dr. Bing Chi. Dr. Chi?
Hello.
Hello, yes, we can hear you fine.
Okay, that's great. So somehow my internet connection has some problem this evening. So just in case my connection is broken and I have to rejoin, so I apologize for that. So shall we start?
Of course, please.
Okay, so good morning, good afternoon, good evening, and welcome to QCrypt 2022, and this is the section 2 of day 2. We have 3 experimental talks, and the first one is by Wang Shuang from University of Science and Technology of China. Okay, Shuang, the floor is yours. Please go ahead.
Okay, thank you. Can you hear me?
Yes.
Yes.
Yeah, okay. Good morning, everyone. It's my pleasure to give a contributed talk. I'm Shuang Wang from University of Science and Technology of China. Today, I would like to present tuned-field QKD over 833.8 kilometers fiber, mainly about my recent Nature Photonics paper. For end-to-end QKD without repeaters, there is a fundamental limit. Well, tuned-field QKD builds up a promising rate-distance relationship to overcome this limit. In 2019, 4 groups first demonstrated the feasibility of tuned-field QKD. We are the first one over fiber channels and get 2 kilo BPS cycle K rate over 300 kilometers fiber. After this, our goal with tuned-field QKD is to double the transmission distance of BBS4, assumed by this formula. So my presentation will cover the following aspects: preparations of fiber and single-phone detectors, and the low-noise repeater-like source. Then its measurement and compensation of phase drift. Finally, our results and conclusion. First, the optical fiber is the ultra-low loss one. The superconducting single-phone detectors has a close 60% efficiency with 0.13 Hertz dark count rate. This is a typical structure of tuned-field QKD. There are 2 main experimental challenges. One is the laser source to generate a tuned field. The other is to compensate the phase drift, mainly from fiber channels. Also, a core part, our repeater-like source is based on home-down optical phase-locked loop. Through cloning the phase of the remote accumulator, the wavelength difference between the remote laser and the local laser are substantially zero. With them, further add a feedback phase modulator, further reduce the residual phase noise. One important feature of the source is its high sensitivity without the lead of optical amplifiers, which would inevitably bring extra noise. This is a remote accumulator and local laser in the experiment. Here we first test the source noise without fiber channels with a 1 nanowatt input power, 2 sources locked to the common laser source, and their corresponding output beams interfere on this beam splitter. The left are the interfere outcomes over 400 seconds. The right are the corresponding standard deviation of phase drift rate, which are used to characterize the source noise. These are the results of single laser. These are the results from 2 phase lock laser without feedback phase modulator. The noise level of this source is still 2.5 times of single laser. Then after the feedback phase modulator was added in the source, the noise level almost identical to that of a single laser. So the trim field could be remotely generated with a very high quantity. Compared with other source games, the noise in our repeat-like source is the lowest. We then use this setup to characterize the phase drift of the whole system. The measurement setup could be seen as a large Mahazenja interferometer, whose arms consist of self channel, repeat-like source, and quantum channel. All elements that would introduce phase drift are included, including the laser source, 5 channels. One difficulty of this measurement is the power of the interference outcome. It's very low, only a few nanowatts. We made a high sensitivity detector based on APD. Its sensitivity is less than 5 picowatt with a bandwidth of larger than 100 kilohertz. The output was finally recorded by an oscilloscope. The standard deviation of the phase drift rate over this 20 seconds is about 14 radian per millisecond. To compensate the fast phase drifts, we choose a frame period of 20 microseconds. This is a time sequence. The positron was chopped into a bright reference part and a weak quantum part. The reference part, the estimate region is used to estimate the value of relative drifted phase. The visit indicator is used to indicate the compensated result by showing the visibility of interference. The visibility of interference requires a strong reference process. For long fiber, the stronger the better. Well, the multipath interference noise says the weaker the better. So there is a trade-off of intensity of reference process. We measure the visibility of reference pulse and MPI noise in quantum part of a different intensity of reference process. Obviously, the MPI noise increases linearly with the intensity of reference process, while the visibility of a reference part first increases rapidly, then gradually. So we choose the intensity of 115 phones per pulse. These 4 figures show the stability of the system over different lengths, including the visibility of reference process, quantum beta error rate of quantum process. The longest time was up to 200,000 seconds, about 56 hours. Finally, I would like to make a conclusion with this presentation. Here we present an optimized trim field QKD setup that could tolerate a channel loss beyond 140 dB and obtain a cycle distance over 830 kilometers without the assistance of optical amplifiers. The cycle rate substantially exceeds previous experiments. For example, at 500 kilometers, that of is more than 2 orders of magnitude than previous record. Thus, our result provide a considerable approach towards 1,000 kilometer fibrous quantum K distribution. Okay, thank you very much for your kind attention. If you want to know more details, you can find them in this paper and its supplementary information. If you have any questions, I would be happy to answer it. Thank you.
Great. Thank you, Wang Shuang, for this nice talk. I forgot to mention the rule. So if you have any questions, you can either put in the Q&A box or you can raise your hand after the talk. So any questions from audience?
Any questions here from Taipei? Can raise your hands, use the microphone.
So maybe I ask one question. Shuang, what's the main challenge if we want to apply this scheme in deployed fiber?
Deployed fiber, there are about there are three requirements. One, I think in the deployed fiber, the phase drift rate might be slower than in the lab. The main challenge is about the synchronization of the Alice and Bob, and also other compensation technique such as time polarization and also might be the classical communication. Yeah.
Okay, thank you for your answer. So, okay, we have one question from Naha Solak. Sorry for my pronunciation. So the question is, how do you perform the security analysis of this protocol? I went through the paper, but might have missed it.
Security analysis of the protocol. Yes, the security analysis is in the supplementary information. This protocol is a new protocol based with 4-phase modulated. You can find them in the supplementary information. I remember it's in the first part. Yeah.
Okay, so okay, let's thank the speaker again, and because of time, let's move to the next speaker.
Thank you.
Yeah, thank you. And our next speaker is Zhang Chi, also from USTC. So please go ahead, share your slides, and go forward for your presentation.
Okay. Thank you. Can you hear me?
Yes, we can hear you.
Yes.
Yeah, okay, thank you. Good morning, good afternoon, and good evening, everyone. My name is Zhang from University of Science and Technology of China. I'm glad to be here to give my talk today on QCrypt 2022. And my subject today is experimental side-channel secure quantum key distribution. And this paper has been published in the physical review letters. And first, I'd like to introduce the background of my work. In theory, QKD can provide an unconditionally secure key exchange for remote users. However, in practical QKD systems, side channels may appear due to device imperfections. For example, in this prepare and measure QKD system, hackers may take advantage of these side channels in detections. They can take time shift attack, detector blinding attack, and detector after gate attack, and so on. However, luckily, this can be solved by MDI QKD, which is immune to all attacks on the measurement devices. But the side channels from the source still exist. The practical security can be undermined when there are differences in the side channels of the emitted photons from the transmitter's lab. For example, in a protocol using polarization encoding or phase encoding, there can be imperfections in the side channel space, such as the frequency spectrum, the light emission time, propagation direction, and so on. In such cases, the hackers may acquire the secure keys by just monitoring the side channels only without affecting the encoding space. Well, in this paper, Professor Xiangbin Wang proposed a side channel secure quantum key distribution protocol, which is not only immune to all attacks on the side channel space of emitted photons, but also retains the MDI characteristic by adopting the MDI architecture. On the other hand, DI-QPD can provide side channel security, however, which demands a loophole-free bail test setup. Although there have been some DI-QPD experimental demonstrations, but generally speaking, it still remains experimentally challenging because it requires very efficient single photon detection. Well, back to our protocol. In this protocol, coherent states without any phase randomization are used as a source, so the decoy state assumption is not required. At first, two transmitters, Alice and Bob, prepare a coherent state and only decide on sending or not sending it to Charlie randomly for encoding. Besides, they also send phase reference pulses to estimate the phase drift in the quantum channels. And then Charlie measures the signal pulses and announces which detector clicks. An effective event is one and only one detector clicks. And he also measures phase reference pulses. Next, Alice and Bob keep the bits when the phase differences is below a threshold. Among the preserved bits, they randomly select some test bits to do error test and parameter estimation. Then they distill the remaining effective bits to generate the keys. In this protocol, we assume that when they decide not to send, the vacuum state is perfect. For further detailed analysis, please refer to the whole paper. And here comes our experimental setup, which is shown in this figure. First, we use the time frequency dissemination technology to accurately control the phase difference in the single photon interference of two independent laser sources, which are 50 kilometers apart. The final line width of the two lasers is less than 1 Hertz, and the phase drift of the relative frequency difference is less than 0.1 Hertz per second. And similar to twin field QKD, the relative phase between Alice and Bob is not stable because of the fluctuation of the quantum channel fiber length and the wavelength difference between the two sources. So we adopt strong phase reference pulses, time multiplexed with the quantum signal pulses to estimate the relative phase between Alice and Bob's signal pulses. So here, phase modulator is set to modulate the phase of the reference pulses. And one of the three intensity modulators is set to control the sending and not sending encoding, and the other two intensity modulators are used to modulate the relative intensities between reference and signal pulses. The quantum channel consists of a standard optical fiber spool of 50 kilometers, and the light is then filtered with circulators and interference at Charlie's beam splitter, and then detected by two SNSPDs with a detection efficiency of about 84% and a dark count rate of 3 Hertz. Here is the detailed encoding method in our experiment. The basic period of signal and reference pulses is 1 microsecond. In the time interval, 100 signal pulses are sent in the first 400 nanoseconds as sending or not sending, with 240 picoseconds duration and 4 nanosecond period. No phase modulation is applied to these signal pulses, and in the next 440 nanoseconds, 4 phase reference pulses are sent for estimating the relative phase between Alice's and Bob's fiber channels. And the last 160 nanoseconds is used for the recovering time for the SNSPDs with vacuum state sent. Here is our experimental results. With this setup, we performed the side channel secure QKD over a distance of 0, 20, and 50 kilometers. We choose 10% of the effective bits as test bits to do error estimation, and the phase threshold is optimized to 30 degrees. And the Q bar is around 1.7%, and the final key rate is 173 BPS, considering the effective repetition frequency of 100 megahertz. And our experiment shows that the side channel security of the emitted photon and the measurement device independent security can be simultaneously achieved in the QKD system with matured existing technologies. And with our experimental parameters, it is predicted that more than 170 kilometers distribution distance can be achieved with our setup. Finally, I'd like to make some discussion, and we note that the actual state is not a perfect vacuum state when Alice and Bob decides not to send coherent state to Charlie due to the finite extinction ratio of the intensity modulators. And the total extinction ratio of signal pulse to the vacuum is about 70 decibels. And after taking this non-ideal vacuum state into consideration, the revised security rates only decreases by less than 0.1% according to this figure. And also, the security rates may not be high as that of MDI and decoy state BB84 protocols. We note that the lower key rate in our experiment is the price for the high practical security, since we have to use a very weak coherent state to take the worst case analysis in this protocol to guarantee the side channel secure property. Well, okay, that's all of my talk. Thank you for your attention.
Oh, thank you very much for the nice talk. Are there any questions from audience?
Any questions here? Do you have any questions online?
Okay, I found one question from Zhang Yuzhe. And the question is, simulation results shows the distance can be up to 160 kilometers. What are the main challenge in getting longer distance experimentally?
Thank you for the question. Yes, as the simulation results, it can say that the distance can be up to 160 kilometers. Well, as I said, as we do not use the decoy state assumption, and we have to use the worst case analysis. So, and to guarantee the side channel security, we have to use very weak coherent state. And you can see that our intensity is, or the mean photon number per pulse is very low compared to other QPD protocols. So if we want to get longer distance, as I remembered, the optimized intensity will decrease a lot. So it is difficult in experiment to maintain the intensity stability. And then on the other hand, we have to send stronger phase reference pulses to estimating the phase drift. So if the distance gets longer, the intensity of the phase reference pulses gets higher. So there may be some noises such as really scattering background noise. So it will introduce another qubit in the quantum signal pulses. So I hope that helped.
Okay, thanks answers. And there are two more questions in the Q&A box, but because we are running out of time, could you please type your answer in the box for those questions? Thank you. And let's move to the next speaker, Chen Jiupeng, who is also from University of Science and Technology of China. Hi, Jiupeng. Can you share your slide?
This is our next speaker online, Jiupeng Chen. Oh, yeah.
Sorry, can you hear me?
Yes.
Yeah. You now?
Oh, okay.
Yes.
Camera?
Okay. Good morning, everyone. My name is Chen Jiupeng. I'm from the University of Science and Technology of China. It's my pleasure to be here to introduce our work about quantum distribution over 658 kilometers of fiber with distributed vibration sensing. Quantum K distribution offers a theoretical proper way to distribute secure keys. However, the channel loss is an inevitable barrier for long-distance QPD, since a quantum signal cannot be empty field. In order to substantially extend the transmission distance, a twin-field MDI QPD scan was proposed very recently. In the original MDI QPD, the efficiency of two-photon interference is equal to the channel transmittance eta. In the twin-field QKD, the K is generated from a single photon interference. Thus, the efficiency can be improved to square root of the channel transmittance. It was shown in theory with twin-field scan, QKD in commercial fiber can even reach 700 to 800 kilometers. At present, several experimental demonstrations of TF-QPD have been performed by various research groups around the world. The longest distribution distance in the field is 511 kilometers, and the distance recorded in laboratory is averaged to 833 kilometers. Here, I introduce a new application of long-distance TF-QT demonstration, TF-QT with distributed vibration sensing. Next, I will give the details of the experiment. Since the realization of TF-QPD requires high-performance remote single-photon interference, it is necessary to precisely control the relative global phase of the pulses which are sent from Alice and Bob's independent lasers and transmitted through the long-distance fiber links. The global phase difference between two remote fields are decided by the wavelength difference and the fiber length fluctuation. To achieve a stable phase interference, we first need to lock the frequency of the two remote lasers. Second, we must overcome
Professor Chen, are you still? We can't hear you right now. Hello, can you hear us? Because we cannot hear your voice right now. Maybe would you like to try to log in again, or maybe have you mute your mic? But he's still moving, right?
Look like
the
or we can communicate with the chat box first to see if he's still online with us, or maybe.
Hi, Juton, we cannot really hear you.
Maybe it's a problem with the internet connection, because we tried to contact him from through the chat box, but there is no response. So maybe we have him dial in again.
Yeah. Oh,
Back.
okay, come back.
Doesn't. Jobong? Professor Chen?
Yes,
Yeah.
Peng.
I think he just moved the slide by himself. May- Jopong, we cannot hear you. Can you hear us? Maybe there is a connection problem. So if you can hear us, would you like to dial in again? Try to reconnect again because we cannot hear you. We can see you moving your slide, but we cannot hear your voice.
Can you hear? Okay,
Now
hear
we
me?
can,
Yes.
Now can you hear me?
But not stable.
Not stable.
Oh, I
Now
can.
can you hear?
I think.
Oh, okay.
we miss most of your presentation.
The protocol used in our experiment is the sending-allow sending TFQT protocol. In this protocol, N is will randomly choose X basis or Z basis with probabilities Px and Pz. For the X basis, Alice and Bob will randomly prepare and send out the decoy state pods. For the Z basis, Alice and Bob randomly decide to send out the weak current state pods or loud sending. Here is our schematic of the experiment setup. For the twin field light source part, and in Alice or Bob's lab, oscillator laser is locked to an ultra-low expansion glass cavity to achieve subhertz dynamics by using the pump jar hole technique. After PDH locking, a 500 MHz AOM with adjustable carrier frequency is inserted to eliminate the frequency difference of the two stable lasers. Then the unstable light source are split to two parts respectively. One is used for QED, the other is sent to the other user via frequency calibration link for heat-die interference. Bi-EDFAs are inserted every 50 kilometers to maintain the power of the transmitted light. Two AOMs with the fixed carrier frequency of 40 MHz and 70 MHz are inserted at both ends of the link to force the reflection in the channel. In the QQD part, the light is encoded with two phase modulators and four intensity modulators, and autolulated to single photon level with an autolulator. The light is finally sent to Charlie through the quantum channel. Charlie uses a DWDM, a circulator, to force the noise before the PBS and the BS. The interference results are detected by superconducting nanowire interphoton detectors and recorded by a time tagger. Additionally, we inserted the program-controlled PZT vibration generators in the fiber channels to investigate the vibration perturbations. The light is modulated to a pattern light. The single photon level quantum signal pods are time multiplexed with strong reference pods. In a basic period of 1 microsecond, 100 signal pods are encoded for QQD. 4 strong reference pods are encoded for calculating the relative phase difference of the fiber links. And the relative phase difference of the fiber links is compensated in post-data processing. In addition, one vacuum pulse is encoded for recovery of XN SPDs. After realization of the experimental setup, we first explored the longest possible TFQD distribution distance with our experimental setup. 658 kilometers at low loss fiber spurs with a total loss of 106 dB is used as a quantum channel. The component loss and insertion loss is optimized to 1.3 dB in Charlie. Then we adopt the high performance SNSPDs with detection efficiency of about 80% and an effective dark count rate of about 4 Hz to detect the interference. And set a time gate of 0.3 nanosecond to suppress the noise. The final noise is optimized to be 6 times 10 to -9 per pulse, about 80% of which is from radiation scattering. In about 28 hours, a total of 1 times 10 to 13 signals are sent at the 100 megahertz effective system frequency, yielding about 5.3 times 10 to 61 detections. The final cycle key rate is then calculated to 0.092 bps by considering finite data size effects. Then we modulate the PZT vibration generators with fixed frequencies to simulate the vibration perturbations in the channel. In the case that the PZT vibration takes place in the quantum channel, the phase drift is recovered by calculating the relative phase difference with the phase reference pulse. We set the modulation to sinusoidal signal with selected frequencies of 1 Hz, 10 Hz, 100 Hz, and 1 kHz respectively, which is a frequency range of interest in seismic and acoustic wave sensing. The blue curve indicates the recovered relative phase variation signal, and the gray dotted line indicates the modulation signal of the artificial vibrocytes. In the time domain, the recovered phase variation perfectly matches the active modulation signal. In the case that the PZT vibration takes place in the frequency calibration channel, we set the channel length to 0, 200, and 500 kilometers respectively, and install the vibrocytes at anions with different vibration frequencies. Here, the vibration signal is recovered by electronically decoding phase perturbations of the RF signal of T-Dan. The blue curve and the red curve indicates the recovered phase variation signals of anions and bob. And the gray dotted line indicates the modulation signal of artificial vibrocytes. The recovered phase variation shows a frequency and the waveform exactly the same as that of the driving signal in all the fiber lengths. The vibrocyte position is measured by calculating the relative time delay of the vibration signals at anions and bob. The precision of location is better than 1 kilometer. Which is mainly limited by the sampling rate of our phase measurements. That's all the content of my talk. Thank you for your attention.
Okay, thank you, Zhu Peng, for the nice talk, even though the difficulty over the internet connection. So any questions from audience? Okay, I have one question here from Lin Jinping. Could the system sense the vibration signal and transmit the quantum signal simultaneously?
Yes. Actually, we actually the quantum channel can be used to sense the vibration. In the experiment, here in the experiment we inserted vibrocytes in the quantum channel to modulate the vibration in the quantum channel. We set the modulation signal. The signal frequency is frequency of 1 Hz, 10 Hz, 100 Hz, and 1 kHz sinusoidal signal. The blue curve indicates the recovered relative phase variation signal, and the gray dotted line indicates the modulation signal. In the time domain, the recovered phase variation perfectly matches the active modulation signal.
Okay, so thank you for the answer. Any other questions?
Any questions here? Oh yeah, I think we have a question here on site.
But this is not exactly a question, but maybe more a reminder from the organization side. So especially to the last speaker just now, we have not received the video, the pre-recorded video from you. So I guess it will be really useful if you could send it to us as soon as possible to make up at least the loss that we had just now. Right? Because we were not really able to follow because of this intermittent internet disruptions. So if you could upload the video to us, that will at least make up for this loss. Thank you very much. Same thing for the other speakers. I think there's also another video from this session that has not been uploaded. Thank you.
Sorry, the voice is low. I can't hear clear.
Any other questions?
Okay. Okay, if no other question, let's thank all the speaker again. So we are a little bit over time, but I think we survive. Thank you.
Okay, thank you.
Yeah, thank you, Dr. Chi, for moderating the session, and thank you.
Thank you.
For the perspective.